Good morning, everyone. Today I'm going to talk about new chapters, electric force and fields. And especially today I'm going to talk about electric force called Coulomb's law. Okay. So Coulomb's law is basically same as a gravitational, force law that you already learned previously last semester, I believe, right? So if you remember gravitational force, that is gravitational force is given by g, a constant like pi or just constant, and then m1 times m2 divided by r squared. So where m1 is the mass of an object 1 and m2 is the mass of an object 2, and then r is the distance between two objects. So in other words, if there's a two masses, then they're always attractive force toward each other. So from M1's point of view, M2 is attracted toward it. And then from M2's point of view, M1 is attracting M2 toward it. So that's a gravitational force. So as long as you have two objects, and then as long as they have their own masses, there's always attractive forces between these two objects. One simple example is between the Earth and you. Earth has a mass of the Earth, so the gravitational force between you and the Earth is gonna be m over Earth, and then small m is your mass, for example, and then divided by r e squared, which is the radius of the Earth, right? So this is a gravitational force between you and the Earth, which is we call it, wait, which is m times g. So in other words, your g is gonna be combination of these three numbers. G is a very small number, and then me is the mass of the Earth. Re is the distance between you and the Earth, which is again radius of the Earth. So for the same logic, you can also find gravity, G. So this is G of the Earth. But you can also find the G of a moon. How? Simply large G times the mass of the moon and then radius of the moon square. So basically you can find any planet's gravity using this formula. Again, your weight is just one example of this gravitational force. And then interestingly, a lot of physics force is based on this formula. And then today, what you're gonna learn, electrical force based on Coulomb's law, it has a very similar relationship with this. So call this is an electrical force, which is instead of a G, we'll use another coefficient K. And then instead of a mass, you have a charge of object 1 and then charge object 2 divided by same r squared, distance between two charges. So you will see mathematically this electrical force is exactly the same as the gravitational force, right? Except that what? Instead of a g, you have a different coefficient k. Instead of a mass, you have a charges. That's the only differences. And sorry, there's another differences is what? Gravitational force is always a attractive force toward each other. But electrical force, as you know, if you have a plus plus charge, minus minus charge, then you have a repulsive force. But if you have a plus minus, then that is a attractive force, which is the same as a gravitational force, right? So this is only one differences, and then the other one is mathematically equivalent, but you have a different physical meaning, K and then Q's. Okay. So we have developed the model of charges and electric forces, right? And then that force law is called Coulomb's law, right? So then we will use the magnitude of the charge, not the sign, but they said not the sign, but if you consider sign, that will change the direction of the force, right? So Coulomb's law is a very straightforward. Again, F1 on 2, so charge 1 on charge 2. And of course, they are the same. Why? Because again, this is the Newton's second law, right? Charge 2 on A, their magnitude are the same. That's why they said they use these absolute values here, right? But if because they use the absolute value to compare their magnitude, right? But from charge one's point of view, let's assume charge one is a proton, charge two is an electron, and then charge one's point of view, the force is to the left. Charge two's point of view, the force is to the left. Sorry, charge one's point of view, force is to the right, right? So their force directions are opposite, but the magnitude are the same. And again, K is a constant. It's 8.99 times 10 to 8. But you can simply say this is a 9. Okay. And then this K is basically, I will introduce later. It's another defined with another variables, which is a epsilon 0. It's basically this K is a 4 phi epsilon 0. But I will introduce this concept later. But you can, for now, this is enough. K is a 1 over 4 phi epsilon 0, and the K value is a 9. And the direction, the forces are directly along the line joining two particles. Basically, the force, you have a proton, let's assume you have an electron, and then the force is acting along this line, right? And then these forces are repulsive if they have the same charges, and attractive if they have opposite charges, right? So this is attractive force if they have the same charge signs, then they will have a repulsive force, right? And then Coulomb's law describes the forces between two charged particles, like a gravitational force is between two mass particles, right? So Coulomb's law applies only to point charges. So point charges here means even though the physical, shape of a charge is, for example, it's a sphere. So actually, we don't know where the actual charge is located, right? Then we assume this is a point charge, meaning that all charges are located at the center of the sphere. Right? So object can be considered point charges if they are much smaller than the distance between them, right? So you can assume this is just point, even though sometimes you draw it with a big, sphere, but assume this is just point, and then all charges are located at the point. And again, because this is a plus charge Q1, Q2, so then the forces are repulsive along this line, right? So force charge 1 on 2 is to this direction, and the force charge 2 on 1 is this direction, and you see the direction is the opposite. The magnitude, which is the length of this arrow, are the same. And then of course F1 on 2 equals F2 on 2, 2 on 1 equals again K times Q1, Q2 divided by R squared, assuming they have the all positive numbers here, right? That's Coulomb's law, very straightforward and very simple, right? So Coulomb's law again looks like Newton's law. It's the same, right? And then the direction of the force is determined by the second part of the Coulomb's law, which is the sign. That's not, I don't think you need a lot, additional explanation for that. Same charge, it repels, different charge attract each other, right? So again, electric force is a force. So like other forces that you learn in physics 1, you can superimpose it. So in other words, each electric force are force and vector. So you have to add, if you have a multiple forces acting on one charges, you have to add these vectors by adding, their vector sums, right? And then of course each force is given by Coulomb's law. So then now we have two charges of sphere 2. But the charge of sphere 2 is twice, that is a sphere 1. So this is 2 times charge. Which vector below shows the force of 2 on 1? So you already know F1 on 2 is this much. So what is the magnitude of 1 on 2? Let's say the charge, small charge is Q. Large charge on sphere 2 is a large Q. So then what is F1 on 2? It's K, small q, large Q divided by R square, where R is the distance between these two charges. And then we are looking for, what is the force? 2 on 1. And then that is again same Q over R square. The only difference is this force is to the right, and then this force is to the left. Their directions are different, but the magnitude, these two forces are the same. And again, this is simply Newton's third law. And the second question, the charge of sphere 2 is again twice that of the sphere 1. So I will assume this is a Q, and I will assume this has a 2Q, right? Because it's twice. And then which vector below shows the force of 1 on 2 if the distance between the spheres are reduced by half, right? So initially we are looking for, so the original force 1 on 2, sorry, original force 1 on 2, F1 on 2 will be what? Q, 2Q, right? Of course, you have K divided by R squared. That's the original force. But the now second case is your plus charge here with a small q. And then your second charge is actually halfway with a 2Q. So then your new force gotta be what? K times Q, 2Q. Nothing changes here, right? Because you didn't change your charges. Divided by, instead of R square, you have a R over 2 square, right? So then, of course, if your distance is a closer, the force gotta be stronger. So how many times the question is proportional to 1 over R squared, right? So your distance is 2 times smaller, your force will be 4 times greater. So the answer is gonna be 4 times greater force. In other words, your answer is 4 times over this line. So this is, I believe, 1, 2, 3 times. So 4 times. So I think this is these two are the same length. It's the same force. So this is a 2 times force, none of this, right? So that you have to have a 4 times greater force, right? And then which of the 3 right-hand charges experience the largest force? Again, the same. Case number 1, what is the force? K times large Q and small q divided by R squared. So I'll call this is F1. This is F1. So F2, case number 2, what is your F2? Again, K, Q same, but now you increase your charge 2 times more. So now it's a 2Q divided by R is a 2R squared, right? So then if you rewrite this one, if you take the all, numbers in front, you have a still K, Q, small q, but now you have a 2 in front, so I'll take the 2 in front. And then you have a 4R squared bottom, so you still have a R squared. So instead of, you have a 4 in front. So then this is a 1/2 times all this thing is what? F1. So that's a force, right? And the third one you see here, case number 3, your F3 is gonna be Q, and instead of 2Q now, this time 4Q, of course you have a K here, divided by 2R square. And we do the same thing. You have a K, you have a Q, you have a small q, but the number 4 in front, I will bring it back to here this time. And then you have a r square and 4. So you will cancel, and then this is exactly same as a f1. So first case and the third case, they are the same force. And the second case is actually half of them. Right? So the answer is a E. So the similar question, but it's a little bit trickier. An identical small, positive charge. So this is also charge Q as well, black dot, right? Small charge Q, small charge Q, small charge Q, small charge Q, right? In which case the forces on the small charge is the largest. So again, it's the same thing, exactly same thing. F1 is a K times a Q and another Q over R squared. F2 is gonna be K, Q, Q, but now 2R squared. So if you take the 4 in front, this is gonna be 1 over 4 times F1, right? And the third one, F3, is gonna be K, Q. First one is 2Q, and the second one is a Q, and the third one is a R, right? So it's a R squared. So then now you have a 2 in front, and then K, Q, Q, R squared. Again, this is a F1, so it's a 2 times greater, right? Then F1. And the last one is gonna be F4. Of course, you don't need to solve it now, right? Because why? You increase the distance to 2 times. Then what will happen? The force, oh, sorry, here it was 2Q. So it's basically 2, so it's a half, sorry. So then now, K times a Q over 2R squared. This is a 1 over force, F1. So the answer is a C. It's the greatest force, right? And the next one is kind of a hard, but we can, talk about it. We can think about it quickly. So the following case is identical small positive charge. So this is a proton, right? It's placed at the black dot. In which case the force on the small charge is largest. So now, before we solve it, you have to think about the direction of each forces first. Because from the black dot's point of view, there are two forces, right? By one proton, by two charges for each cases, right? So for example, case A, the force acting on this proton is to the right, right? The force due to this proton is to the right. And then the force due to this electron is also to the right, right? So you have two forces with the same direction, so then you have to add these forces. We'll come back to this case. But how about the case B? Because again, this is a proton. The negative charge will attract it. The proton will repel it, right? So the two forces are acting opposite direction, so they kind of cancel, so it can be largest. And then how about C? Force due to the closure charge to the left. And then how about the second charge? It's also to the left as well, right? So you have to kind of add these two forces because these two forces are the same direction. So I will come back to C. How about D? Attractive to the left and another attractive to the right, and then they will exactly cancel out. So the D, you see the forces will be 0. So then now your question is which one has a greater force? Case A or case C? Let's think about it. So let's assume case A, this is a Q, and this is Q, this is Q. Of course, this is minus Q. And then again, this is Q, Q, Q. So then now, let's say the distance from here to here is R. Here to here is R. So the same distance R and R. So what is the force 1 due to the plus charge to the right? That's simply K times Q over R squared. And then how about the second force? It's also to the right. So basically this is a plus K Q over R squared. So you basically add two forces, same magnitude. But how about the case C? The first force due to this first charge is going to be exactly same as the force up there, right? These two forces are equal. But how about the force due to the second charge? K, Q, same, but the distance for this case is now 2r. So this is a 2r squared, right? So the second force, in this case, is much smaller, 4 times actually smaller than this force. So the answer is A. The first force has the greatest force. And then what is the direction of the force on charge minus Q? Here. So again, it's a very similar question like the previous one. From minus charge, small charge Q's point of view, there are two forces acting on it. Due to this negative charge, you will have a repulsive force to the right. And then due to this proton, you have a attractive force to the left. So the question is which force is greater? Because they have the same charges, right? It only matters about distance. So the plus charge, big charge Q, plus Q, is farther than this distance. So this force is smaller. So the answer is to the right. Minus large Q charge applies a stronger force because it's a closure. And then now let's add actual electric forces with the numbers, okay, in one-dimensional space. Now let's assume you have two 10 nanocoulomb charged particles are 2 centimeters apart. So that means, okay, you have two 10 nanocoulomb charged 2 centimeters apart. So this is a 10 nanocoulomb, and the other one is also 10 nanocoulomb. So distance between these two is 2 centimeters. Right, 2 centimeters, right? And then what is the net force on a 1 nanocoulomb charge midway between them? So that means the distance from here to here is 1 centimeter, and then the other one here to here is also 1 centimeter as well. But this time you can of course calculate the both forces, right? For example, what is the force due to this Q1 charge? Again, K. Q1 is 10 nanocoulomb. So 10 times 10 to minus 9 because it's a nanocoulomb. And then the other one is a charge here is 1 times 10 to minus nanocoulomb. Divided by R is 0.01 centimeter, which is 0.01 meter, which is 1 centimeter square. So this is going to be the force to the left. But however, there's also same amount of force to the right due to this Q2. So the net force will be 0, and then they will cancel each other. So the net force for the first case is straightforward, and that's going to be 0. Right? But how about the second case? So second case, what is the net force if the charged particle on the right is replaced by minus 10 nanocoulomb? So now this is a 10 minus nanocoulomb. So you again have a 10 nanocoulomb. You now have a minus 10 nanocoulomb. And again, this is, I believe, 1 nanocoulomb. But the thing is now, your force due to this proton is to the right. And then your force due to this electron is also to the right. So then you have to add these two forces, right? So your answer, your net force is going to be what? K times Q1 is 10 times 10 to minus 9. This is a Q1. And then Q2 is 1 times 10 to minus 9 nanocoulomb. And then distance from here to here is again 0.01 meter square. So this is our first force. And the second force is exactly same as this force. So your final answer will be times 2. Right? That's gonna be your final answer. And then assuming your K is again 9. Your K is 9 times 10, 9. And then first charge, second charge, distance square, and then you have a first force, and your answer again will be times 2. So that's gonna be your final answer, and the direction is to the right. And then, what is the direction of the net force on the charge at the lower left charge? Again, how many forces acting on this proton this time? There are 3 forces acting on it, right? First force is due to this proton, and the second force is due to this proton, and the third force is due to this proton. So basically, they are, kindly draw the all pictures, right? This force is gonna be due to charge number 1, because this is a plus plus, so you have a repulsive force, right? And then due to this proton, you have a repulsive force to the left. And then due to this proton, you have another force this direction. And then, but you see the sum, vector sum of A and C is also along B vector, right? So basically you're adding 2 vectors along B line. So your final answer will be B. How about here? Which is the direction of the net force on the charge at the top. So then again, this charge will feel 2 forces. Due to this proton, it will feel repulsive force. And then due to this force, negative charge, you have a repulsive force to the left, to this way, right? So the net force, which is a vector sum of these 2 arrows, is gonna be to the right. So the answer is right. And the last example we have today is also very simple. You will see you have a very small plastic sphere. Charge is a minus 10 nanocoulomb. So this plastic sphere is has a 10 nanocoulomb, minus 10 nanocoulomb, and it is held 1 centimeter above of a small glass bead at rest on a table. So you have a glass bead here. The bead has a mass of 15 milligram and then charge of 10 nanocoulomb. It has a 10 nanocoulomb, right? Will the glass bead lift up the plastic sphere? So then now we are interested in net force acting on this plastic sphere. So what force is acting on this plastic sphere? There are actually 2 forces, right? Which is a weight of this plastic sphere. Weight is simply mg, right? And then what else force is what else force is acting on the plastic is electrical force, right? Acting, because this is a minus and this is plus. Sorry, the electric force is acting downward as well, right? The plastic, right? And then how about the bead? I'm sorry, the glass. Glass have 2 forces, right? It's a weight acting downwards, and then electrical force between this plastic and glass, right? So then the net force is upward, and then this electrical force is again simple. K times Q1 is 10 nanocoulomb times 9 to 9, 10 to 9. I'm not gonna write it down here, but another one is 10 divided by R is 0.01 centimeter square. So of course you have a 10 to minus 18 here, right? So your question is simply this force, electrical force, is greater than the mass of it, right? So the electrical force, you can calculate it quickly and simply, right? K, I think they don't give you the number, 9 times 10, 9. And then one was minus 10 nanocoulomb, and the other one is another 10 nanocoulomb. So that's gotta be this force. And then your weight will be mass times gravity. So mass is, I think it's a milligram scale. Yeah, milligram, 10 to minus 3. And then distance is G is 10. So you have this force. Then you see which force is greater. F112 exceeds the B's weight by the factor of 60 times. So this is 10 to minus 3. This is 10 to minus 4. So the glass bead will flip over. Okay, so what we did today is about the Coulomb's law, right? Coulomb's law is about the electrical force between two charges, which is very similar with the gravitational force between two masses, okay? And then the only difference is instead of a mass, you use a charge, right? And then it can be either attractive and repulsive force depending on their size, okay? And then I recommend again, go over examples by yourself and then let me know if you have any question.